Hello everyone. Good morning, good afternoon, and good evening. I am Asma Shindi. I am a petroleum engineer graduated from American University of Ras Al Khaimah. On behalf of BioPetro Arab Oil and Gas Academy and SPE Egypt section, I would like to welcome all of you to the second session of our short course Cement Evaluation: The Basics and Beyond, presented by distinguished speaker Mr. Kirk Harris. Our course is 4 webinars and 4 quizzes and a final exam. Certificates are provided if you have scored higher than 70% of the total grade. Before I present our speaker, I would like to remind you if you have any questions, please drop them in the Q&A box. And if you want to ask a question on the chat box, please keep the chat box professional. Now, our speaker is Mr. Kirk Harris. He is the technical advisor for Throwbond LLC, which provides technical support for cementing and bond long interpretation. Prior to his work of Throwbond, Kirk was the global cementing advisor for Occidental Petroleum, Talisman Energy, and Repsol. He began his career at Halliburton, where he worked as cementer, operation and research engineer, and technology manager. He has been the regional cementing advisor for Asia Pacific, the North Sea, Europe, Africa, the Permian Basin, and the Gulf of Mexico. Kerr graduated from Purdue University with a bachelor's degree in civil engineering. Today, our session will be on ultrasonic cement log basics and interpretation, so please pay attention and help me to welcome Mr. Kirk Harris. Mr. Kirk, the mic is yours.
Thank you so much for the introduction. And again, it's a privilege to be here for our second session on the ultrasonic log. As a matter of fact, just this week, I received a series of logs that I've been interpreting, and the oil company decided, and I think rightly so, it's an interesting question, and that is they decided they were going to use the ultrasonic log as the log that they would use to evaluate their cement jobs. I'm working with another client, working with them this week. They've chosen Baker's SBT as their log of choice. And then many others use the radio bond log or the basic bond log. So we're going to focus back on the ultrasonic log, kind of compare it and see the things that we can get from it that we can't get from other places. Now, we're going to do this for the next hour to hour and 15 minutes, I think, or as long as anyone wants to hang around. But I'm looking now at the participants who are here. I see some familiar names. And what I'm going to ask you to do, I'm going to be asking you some questions. And if you use your chat feature, I'll be seeing your replies and we can have a bit of a conversation as we walk through the basics and beyond the basics of the ultrasonic log. This next slide, I don't know what you can see. Can you see anything there? Have you ever? You can use your chat. This is to practice your chat feature. Those of you who are listening by YouTube or by listening to a recording of this are going to say, why is he asking all these questions? Well, even while you're listening to the recording, you can answer these questions. Well, good. You should see nothing. Do you ever feel like this? Do you ever experience this? I know that when sometimes I get up in the middle of the night, I can't sleep because I'm thinking about bond logs. And so I get up and I go to the kitchen to get something to eat, and all of the lights are out. I can't see anything. And I don't want to turn the light on. I don't know why I don't turn the light on, but I try to find my way to the kitchen. And I'm looking like this. And how do I get there? I cannot see. Down hole, we cannot see either. The purpose of what we're talking about is to how to evaluate a cement job, and we cannot see down hole. It is blank. And so I find that what I usually do, I sometimes even close my eyes and I use my hands and I use my memory to find my way to the kitchen. I don't use too many other senses, just touch, and I remember where I'm going. And when I do that, I usually run into something. I've hurt myself a couple times. So it doesn't work real well, but I use other senses. When we talk about the ultrasonic log, we come out of the dark. Let's go visit an animal called the bat, who also finds himself in the dark and still has to find his way to the kitchen. When you look at the bat here going after the moth or the insect, I'm going to ask you a few questions. I call this the ultrasonic quiz. So give me the answer that you think is correct. True or false? Bats use what is called echolocation to find food. Is the correct term they use echolocation? True or false? This isn't the quiz, by the way, to get your certificate. Okay. I'm not sure when I go to find my food at night what that's called, when I touch the furniture or I find my way, but it is true. It's echolocation. They're sending out a sound wave and they're receiving it back. They're receiving the echo to locate where they're going. I never really thought about going to the kitchen and making sounds and listening for sounds, reflecting to know where I'm going. I have a feeling that would be a disaster. Question 2. At what frequency are these sound waves? At what frequency do bats find moths? What is the frequency? And I'll give you a range of frequency. What do you think? The human ear can hear a frequency of 20 kilohertz. It's very high. It's actually the frequency that bond logs work at. And we can hear, if the sound is less than 20 kilohertz, we can hear it. What do the bats send out? It is HF. It is high frequency. Thank you. I've always heard it's about 140 kilohertz. Some more study shows it can be even higher, but some operate lower. These are ultrasonic signals that bats send out that reflect off the moth, that come back to the ear, where they then sense with their brain where it is and to some degree what it is. Okay, you're doing pretty well. At what frequency do ultrasonic logs find cement? The logs we're about to look at what frequency? We're going to do a quick review of bond logs, which operate at 18 to 20 kilohertz. We do have other tools, such as the segmented bond tool that operates at different frequencies. What is the frequency that ultrasonic logs operate at? Waiting for the answer. 200 to 700 kilohertz. Thank you. And I know some of you are chatting addressed to all panelists. I don't know if you can change that to all panelists and attendees. You don't have to, but if you do, everyone can see your comments. A very high frequency, the logging tool are. Well, here's a random question. Are bats blind? Can bats see? Are bats blind is the question. I'm sorry. We learn many things about life that are incorrect when we're young. Blind as a bat is not true. Bats can see. They just happen to be operating in the dark, so they can't see really well in the dark, but they can see. Bats are not blind. And the final question, are bats good interpreters? They're sending out a signal. They're receiving a reflection, an echo. We're going to be looking at the ultrasonic log and the kind of echo we receive when we run the ultrasonic. Are they good interpreters? I don't know if they are or not, but I think so. I think so. Number one, they still survive. This is how they eat food. Not all of them. Some of them get food in different ways, but many. This is how they get food, so they survive. So I guess they can do this. But when I was a small child, I actually did an experiment that proved this. I don't know if any of you have ever done this or if you lived in an area that had bats, but in the place in the USA where I lived, there were many bats. And my brother and I would go out in the evening, early evening. It was getting dark, and the bats were out trying to find insects. So we would take rocks, and we weren't trying to hit the bats. We were good children, but we would pick up the rocks and throw them in the air, and we would watch the bat come to get the rock. And when I think about that, we would throw the rock and the bat would go right for the rock. However, he never hit the rock. He always would veer off at the last minute. He thought he was seeing a moth and he went right to it, but it seemed as when they got close, their ability to reflect, maybe they were picking up the fast formation of the rock, but they were hitting something much more dense than what they would normally eat, and so they would never hit the rock. When I was a child, I must have thrown 10,000 rocks in the air. This is how bored we were as children, I guess. But the bat, very, very good interpreter, I think. This is the CBL. This is what we talked about last week. The agenda for today, we're going to talk about very quickly how we interpret the ultrasonic overall, the specifics of the ultrasonic, how it works, and then in a more advanced state, how we use what you'll see is a very complex log. How we do more advanced interpretation, how we determine if what we're seeing is really what we're seeing, or is it a rock being thrown in the air? Let's review the CBL very quickly. You're going to see a huge difference in the complexity of these logs. We only have 5 curves on the CBL, if you will recall. Can you name those? This dark line here on the left is the very dark one on the left. That is the gamma ray. The dotted line next to it and the gamma ray is giving us just the natural radiation or the radiation of the form of the well bore. So it's really telling us about the formations. The dotted line is the transit time from when I fire a signal, when do I receive it back. The hashed line is the casing collar locator. That's 3. In the middle is the all famous amplitude. It's the strength of the first arrival that we receive on the CBL. And we talked about last week, we must be very, very careful using the amplitude. And then the final curve is on the right, a history of the wave. Time from left to right, depth up and down the well. These are the signals coming in, the ring and the resonance, and it is called, thank you, the variable density log, the VDL. When it comes to the ultrasonic, And I will not get into the specifics. We will talk about it in advanced interpretation, which we'll be looking at next week. We will receive ultrasonic logs from Schlumberger, from Halliburton, from Weatherford, and from Reed. These are the four I am aware of, although I'm sure other tools are out there and have been licensed. These are the main providers of ultrasonic logs. Look at this log. I bring this up because this is the header of an ultrasonic log. Not all are this complicated. Some are too simple, perhaps. We'll look at some of those. But if I'm an interpreter and I receive this log, I'm going to look at this and see that there are 38 headers on this particular composite log, we call it, with all the curves. This is enough right here to scare me back into my office and to call the logging company and say, would you just tell me what I've got, because I'm not even going to touch the complexity of this log. And what I want to say to you, even though there are 38 headers, do not be scared, do not be afraid. As complex or as much processed as this tool is, we're still talking about the simplicity of a sound wave going out, reflecting, and coming back. And we process that wave much more with the ultrasonic, but do not be afraid. We can interpret this log. How do we interpret? We discussed this last week. We're going to interpret the bond log and the ultrasonic log in a very similar overall general manner. And we do it using the 5 C's. Now you will see when we get into the log and what it contains, we're going to have to pay special attention to some other details. We're going to have more information to process. But when it comes to interpreting the log, we're going to interpret and I look at ultrasonics all the time, I still use the 5 C's. If anyone can help me or remember what the 5 C's are, there are 5 steps. We laugh and say coffee is the 6th step. To be honest, it's not a laughing matter. It truly is the 6th C. Usually when I go into the kitchen and it's dark, I'm bumping around to make coffee. It's the whole purpose. Thank you. We construct. Let's start there. We're already comparing and correlating. Thank you so much. We construct the wellbore. When I construct the wellbore, here's an ultrasonic log, a very simple, this is not the composite log. This is a simple abbreviated log, which is showing me the acoustic impedance and the cement maps. We'll look at the details of the log in just a minute. But when I construct this log, I'm looking at things such as what cement was used, what casing was used, what formations are in the wellbore, what logging fluids are in the wellbore. And I draw a picture of it in my mind. Once again, I'm working on several ultrasonic logs. I promise you they are impossible to interpret in the way that we want to interpret, which is to understand what is going on in the wellbore. They are impossible without having constructed the wellbore. The construction was too complicated to look at the log and pretend that we could know everything going on without understanding the casing, cement, formations, and wellbore fluid. However, remember this, we go out and run logs, and often we interpret them without constructing the wellbore. Sometimes we're forced to because we have no information about the wellbore, but we need to start, I don't want to say demanding, but we need to start looking to construct the wellbore as the first and foremost step in the process. Step 2, some of you mentioned, compare sections of the log. Very simple. Thank you. It's Jamel. Construct, compare, correlate. Consider and conclude. Well, let's compare. Very simple, the comparison. Bad and good. As we'll see, the ultrasonic log will process colors such that your eyes are drawn, and it's easy, not always correct, but it's easy to see bad and good, what appears that way. We compare that just by looking up and down. And then we correlate at the points of change. We correlate where it goes from good, or from average to bad, or from good to really good. Just whenever we have a change, here is a dramatic change, we now look left to right and we correlate, and we see very clearly in this case, we correlate right at a spike, which is a gamma spike. And we correlate in this case to the gamma. We then consider the Wellbore effects. I do not want to complicate it. I always talk about 35 effects that occur in Wellbores. We're going to start narrowing that down to about 10 as we talk about it in the future, because almost always we have to check 10. Consider Wellbore effects. Let's look at a couple as it relates to the ultrasonic. This is a microannulus caused by new casing. We know this. This is kind of a famous log. This is an old version of the ultrasonic. Black is high acoustic impedance, or is cement. White is not cement. And look where it occurs. If you go left to, and you go up and down, you can compare, you go left and right, you see that the change occurs at collars. And what we've done in this case, we placed one joint of brand new mill varnish casing into this test well. When we logged it, we could pick up that one joint of casing where mill varnish was not removed. This is not always the case, and some will debate that, hey, I've got fairly new casing and I get a good bond log, and that is a good thing. But many, many times, new casing will give us a poor log and will be misinterpreted. That is the same with the bond log as it is with the ultrasonic. Here's another example that I'm showing. Probably could get a little more specific here, but just for the purposes, this is actually a log and an isolation scanner log. So it does contain it is ultrasonics, and it does contain an ultrasonic log, but it also contains something called excuse that. It also contains an area, the second track from the right, the very colorful track, that is a flexural attenuation track. We'll talk about that in a bit. But in the liner lap, just come over to the right and you'll see blue is no cement, brown is cement. This is something often we will see in a liner lap casing situation, and we'll talk about why that is. But I cannot always interpret. I have to consider if I'm in a liner lap, even on the ultrasonic, that can make a difference. And then after we consider, we conclude with what and why. Here's kind of a famous log I've shown before, but when we get to the bottom of this correlation that we've just shown, we find we have an overpressured hot dolomite that is cross-flowing, and our conclusions that we want to come up with are always why or what is going on. And I ended last session showing this log and showing now that we knew what went on, we were able to perforate this well and fix it. For the next 20 wells we were to drill in this drilling program, we understood what was going on here, started doing some things like running external casing packers to get perfect cement jobs. When you know what's going on, you can fix it and you can make the next well better. That's why it's important to know what's going on. So let's move to the ultrasonics. A different game now. Instead of sending a sound wave out, reflecting it, and 3 or 5 feet away listening for it, we're now going to, and that sound wave going in all directions, we're now going to pinpoint to some degree. We're going to pinpoint that sound wave. And so we're going to rotate our rotating head, and we're going to spin it around. We're actually going to spin it at about 7.5 rotations per second as we're coming up, logging up the well, and we're going to take readings all around the well bore. Pretty amazing tool. And if I can give you my just upfront opinion, I believe the ultrasonic log, it has some limitations. We'll look at those. But I just think the ultrasonic log is a very valuable tool. It has helped me interpret well bores. It has added those features which help give us the answers so many times, and I'll show that to you. It's a very useful tool. So here's the imaging tool. Let me just go to this. Here's the tool right here. You see the tool is run off the bottom, and we can run the CBL and the ultrasonic in tandem, in combination. Just remember that it is probably, we get the best information, the best picture, the best knowledge of the well bore when we run an ultrasonic log with the CBL. That CBL ultrasonic combination gives us very useful information. So we run the ultrasonic log on the bottom of the bond log there in the background, and that rotating head at the bottom. The various tools work differently for the 4 providers that I mentioned before, but in this case, the transducer can be seen at the bottom. In this case, it's inverted, and it's actually bouncing sound waves off of a plate inside the tool so that it's receiving the acoustic impedance information for the logging fluid, the fluid in the well bore. That's very important information. And then it's flipped back, and now we're shooting the sound wave out of the tool and receiving it back at the same transducer. It's almost like taking a tennis ball and throwing it against the wall and catching it. You throw it against the wall and you catch it, and you read the energy that's coming back from that sound wave that you threw at the casing. And then we process that to see what's behind the casing. Different sizes of rotating heads, and again, this will vary. Reed has a tool that they use now that is a SlimHo tool. It's 1 11/16 in diameter, so it can go inside tubings. And so I think that's the only tool. It uses a rotating mirror. We won't get into that for a while. Different casing sizes. And this thing is rotating around. It's got limitations. Extra heavy muds, especially in the oil base, can attenuate the sound that you do not get good data. It has to go through that logging fluid. You see the various parameters there. We're trying to measure the impedance, the acoustic impedance of the material. We'll talk about that. A microannulus, it's very sensitive to a microannulus filled with gas. It's more lenient for a microannulus that's filled with water or mud. And I will just say that although we will theoretically say we cannot see the formation, the truth of the matter is that we will see certain images because of formation interference when we have thin or fast formations or more stresses or certain formation fluids. Everything we're going to talk about again backs up to Snell's law. We send the sound wave out, it hits the casing, and something bounces back. What bounces back is based upon the medium through which it's traveling, and the boundary that it hits. So in this case, if they are different, more bounces back. So you're sending the sound wave through a liquid. It hits the steel casing. You're going to reflect back a large amount of energy, but some energy will pass through. And when it passes through, the next boundary it hits, if it's a solid, more will pass through, less will be reflected. In other words, if there's cement, that wave will go through and less will come back. If it's liquid, you'll get more reflections. And so what's going to happen here, we're going to throw that tennis ball, we're going to throw that sound wave, we're going to receive it back, and what comes back is that first arrival plus all the other reflections that are ping-ponging back and forth across that casing. We get our first arrival back, but more goes through. It reflects off the casing, but guess what? When it comes back the other way, it reflects back. And you get this echo chamber. You get this echo, this sound wave, and when we receive that sound wave back of all of those echoes, some really smart physicists have pieced it together, have developed algorithms so that we can process the wave to see what's behind that casing. Very quickly, the transit time, how fast that sound wave comes back. We can determine the radius of the casing. If our tool is centralized, we'll see the radius of the casing. How much energy comes back is dependent upon the condition of the casing, the inside condition of the casing. For example, if there's a hole in the casing, you're not going to get much energy back. But if it's a good, clean surface, metal surface, you're going to reflect back. So we get our casing condition from that first amplitude. As we go back and forth, reflect, we can determine casing thickness based upon the frequency within the resonance window, the frequency of the peaks. And then we will determine acoustic impedance based upon how much that resonance window decays or how much it rings. If we keep hearing the bell ringing and the casing vibrating, there's no cement. If we see a decay in that sound wave, there is cement. Much of this therefore is based upon the fact that our tool is centralized, that our casing condition is clean, that there are no holes in the casing or cement residue on the casing. That becomes very important. What else is important? The logging fluid itself and what the transit times are there, they have to be aligned for accurate information. So that's why we're measuring it as we go up and down the well bore. Pretty heady stuff. When we do this, and different resonance windows are used, different methods of measuring the logging fluid are used, theoretical versus actual measurements. But at the end of the day, we're going to choose based upon the resonance window, based upon the mud properties, we're going to calculate acoustic impedance. And it's going to be the acoustic impedance of the material just behind the casing. That's what we're reflecting off of, just behind the casing. We're not looking way out. We're looking just right behind the casing. Acoustic impedance is the velocity times the density. It's the velocity of sound through that material multiplied times the density of that material. In metric terms, it calculates Z equals acoustic impedance in megarels. Again, the acoustic impedance of the mud and calculating this is very important. Here are these are actually some Schlumberger numbers. Here's the acoustic impedance of some of these cements. You will see they line up correlate fairly accurately. It's not always true, but very accurately to compressive strength. And so here's the ultrasonic log. You can get very abbreviated logs. You can get much more complicated logs. This is a basic composite log of the ultrasonic. And I'm going to go over just a few of these curves, or a number of them. I'll skip a couple. One is the eccentricity. Based upon the transit time as we circle around, it should all be the same if the tool is centralized. Where it's slightly decentralized, it'll show up in this eccentricity curve. We can tell if we have good data or bad data. We'll use that as a quality control. I skipped over the gamma, I skipped over the casing collar locator, and I skipped over that white track. That white track is a processing flag. It's to flag where you have irregular data, such as at the casing collars. And I've jumped over to the amplitude map. That is the first arrival amplitude. It should be the same up and down the wellbore. It should all be fairly large amplitudes reflecting off that casing. I like to say that map should be shiny, a whitish or yellowish color all the way up and down, no dark spots. Dark spots would be low amplitude, which means we would be reflecting off something besides a good clean steel surface. I will use that to very quickly quality control my bond log. If those dark spots show up there, they will show up in other places. I've skipped over the kind of the middle track there, which is just a schematic of the radius in the wellbore. Here's my casing radius map. Once again, just by transit time, I can see what the radius of my casing is. You'll see red and blue. It will be white will be average, a little more will be blue, a little less will be red. Same is true for my thickness map. If I have a lot of red here, that means my thickness is a little bit less. So you see here, the ultrasonic log not only is going to look at cement, it's giving me a picture of my casing. It's also a casing inspection tool. I have my bond index. Bond index is just graphically showing my amounts of cement yellow, microannulus green, liquid mud or water blue, and red is gas. In my cement impedance map, and I can attach a color to my acoustic impedance. General defaults are gas is 0.3 or less, above that to 2.6 is liquid, above 2.6 is solid. When I go to look at that log, I look at 4 quality control checks. I better say that, I probably should have said this earlier, but I'm not a logging expert, by the way. I'm a cementing expert, I guess. And I've looked at a lot of bond logs, and I've interpreted a lot of logs by comparing the ultrasonic, comparing the bond log to what actually happened. And then I learned a little bit about ultrasonics as I went around teaching with Schlumberger, Halliburton, and others. So what I'm doing here is a quick quality check. There are certain things that have stood out on logs, and you go back and you will see where by doing a quality control, you understand why the data is a bit funny or a bit strange. So while many will do very extensive quality control checks, when I get a log in front of me, or if I were to advise a drilling engineer or a cementing engineer, these are the 4 quick checks that I would do. The first would be to check the fluid properties, then the eccentricity, then the amplitude map, then the radius map. When I'm running the tool, I am measuring the fluid velocity, and I do that with the different tools in different ways. But I'm sending a sound wave out and reading how fast it's going through that, the sound waves going through the liquid. With the Schlumberger tool, I have a plate on the inside of the tool. I invert my transducer and I'm just shooting it off of a metal plate. And it gives me a fluid velocity. This fluid velocity will help me calculate the acoustic impedance, and then it will have a major effect on how I calculate the acoustic impedance, the radius, and and everything else on my log. So I look at this and I want to make sure there's nothing really strange. You see at the top here where I get a shift up at the top here, you'll see that shift on the log, and just understand sometimes that shift is related to density. Now you will not always use this density. Sometimes we'll get some strange numbers here, and that's the question on how to calculate fluid velocity. It's actually being measured here. We know the distances and we know the times, so we're actually measuring it in the tool. These are actual readings of the fluid velocity based upon, well, I guess we're calculating it. We're getting a transit time. We're getting a transit time, and we know the density. So, but we're measuring that velocity. We don't always use this quite often, and I really don't know how often we use. I'm looking at logs now where, I'm gonna be honest, the fluid properties are all over the place. And I've seen some where the fluid properties increase or decrease immediately. You go to the log, it goes straight from cement to no cement. Has nothing to do with cement. It's just the fluid properties, for whatever reason, while they're being measured, went way off. Could be something real, or it could be something with the electronics. But often in all the logs I'm looking at in this series I'm looking at now, we're using a theoretical value for the fluid velocity, for the acoustic impedance. We measure it, but as it wavers back and forth, we end up drawing an average and using a theoretical acoustic impedance for the fluid. So you can look on the log and see if you're using the real or. Number two, we'll check eccentricity. And there are various, I've seen various formulas. Some will say you need to be less than, and this is measured in inches here on this log, that you need to be less than a 0.3 or a 0.5 or a 0.2. It is based upon casing diameter and thickness. So we can check the eccentricity. Now that's going to be funny because the tool can be centered and we can have something on the inside of the casing, which is kind of trying to skew the eccentricity. So we have to even read eccentricity, thinking what's happening in the wellbore. Check number and here's again for eccentricity, if the tool is not centered. I've exaggerated here, but you can imagine if it's not centered, when I try to shoot the sound wave and receive it back, I will only receive it back in one plane. I'll be off centered in all other planes, and some more severe than others. But when I throw the tennis ball to catch the full signal back, I need to be normal to the wellbore. That can only occur when I'm in the center of the wellbore. Therefore, you'll get what we call a double track impedance. This isn't always the case, but it's something to be very concerned about when you see such sharp double tracks in your acoustic impedance. It could be that the tool is E-centered, and actually if you go over to the transit time of the bond log, you see it wandering around a bit. So in this case, it would be very concerning that I'm not having channels over here, but in fact it's eccentricity. We watch out for double track impedance values. Number three, we check the amplitude map, and there you have it there where the dark spots show up. That just means something's going on. The two big things that usually go on, in this case, it's holes in the casing. This is old corroded casing. Or number two, there is cement on the inside of the casing. So instead of reflecting off of steel, you're reflecting off of cement residue. We'll see a little bit later, it may not be cement residue. It may be in an old well, paraffin. That's why we recommend running casing scrapers, especially in the old wells, before we run the log. The inside of the casing will and can affect not only the cement map, but the amplitude map, but the cement map. Number four, we check the radius map. Let's see if I look at it a little closer. I don't. The radius map right here, I don't know if you can see it at this distance, but do you see little lines going up and down? You'll see if you look closely, an observation in these logs is critical as well, but you'll see 2 blue lines, 2 red lines. Matter of fact, if you look closely enough, you're going to see that that radius map, the shapes of those blue and red lines look a lot like the shapes in the cement map. And you have to figure out, why would the radius map look like the cement map? Maybe see it more clearly here. You see the different shapes. At the top, the big squiggly lines. Sometimes the tool, often it's spinning, but sometimes it torques up while it's spinning up the hole, and you'll see that. That's probably what's happening with those squiggly lines. We see it in the amplitude, we see it in the casing radius, we see it in the casing thickness, we see it in the cement map. We see similar patterns. We must use that for quality control to understand what's going on. And in this case, we'll find out that that amplitude map, whatever's causing that amplitude to be low, likely residue on the casing, starts skewing all the other maps. We got to be careful about interpreting the cement map on the right as being purely what we're seeing there. Gets a little tricky at that point. Why do they all look alike? I asked one logging expert, and he said they don't all look alike. And I said, well, they actually do if you'll take a look. He actually told me, I'm not going to look. I'm not going to look because they shouldn't be alike. I asked one of his colleagues a day later that he wouldn't even look at the likenesses. What do you think about the likenesses? He said, well, of course they look alike. They all have the same father. They all were created from the same sound wave, so they should look alike. So we got to be careful because we're processing one wave. And when that amplitude is lowered because of a hole in the casing or because of residue on the casing, it's going to affect all of my interpretation. So let's approach the ultrasonic for the next 20 minutes. This is how we approach it, what we look at, how it differs from the bond log. We'll look quickly at 7 of these and what it looks like when we're interpreting. So when I go to the log, I want to look for acoustic impedance. It is calculated. If it's greater than 2.6, it's usually dark. We can change these on the log, but generally speaking, the defaults greater than 2.6 is cement, less than 2.6 is liquid, less than 0.3 is red. We have all of our maps in the composite. To the left, we have the raw acoustic impedance, all brown as we look to the right of the log. Then we have the bond index, the varying amounts, and then on the far right, we have the processed acoustic impedance. I guess if someone is truly colorblind, they tell me I'm colorblind, but I can see blue and brown there and some green. And that's what we're looking for. The blue, low acoustic impedance, less than 2.6, the dark greater. You see the acoustic impedance changes here. This happens to be a combination. This is a CAST tool, combination of a bond log and the ultrasonic. Do you see the colors? Do you see the dark colors, which would be a solid, the liquid blue, and the red gas. At the top, we have to be careful still, because someone might want to interpret the top, it's all red as gas or liquid as blue. But when we interpret a log, we construct the well and we find out that that is just foam cement at the top. And you see the transition there from solid cement to foam cement, which we're seeing the gas bubbles. Low acoustic impedance, but it's there. When it is low, because lightweight cements, like a foam cement, will have low acoustic impedance, but it will be not just low, it will be variable. Look at as we find top of cement here, not only as you go down the log, and if you look at the colors processed, you'll see that, where although you show a lot of blue in there, there's a lot of brown in there. So what is that? That's low acoustic impedance. But what else is it? It's variable acoustic impedance. Look at the middle curve, which is the average acoustic impedance. It's in megarails, and it goes from low, very uniform, to low. It's still low. It's only about 2 or 3 megarails, but look how variable it gets in lightweight cement. And that's one way we tell if we have cement with the ultrasonic. Not only is the ultrasonic when there's no cement low, but it's very uniform. When it's low and variable, it may be lightweight cement or foam cement. Here's another picture of lightweight cement. This is on a log out of the North Sea. This was interpreted as no cement, but when we constructed the well, we know we had lightweight cement here, but it's debonded. When we run the derivative, Halliburton likes to run the derivative of these, and it shows the variability. And so here's the processed acoustic impedance. You see we start filling in the gaps a bit. But often the ultrasonic for lightweights or debonded will look something like this. It will not look perfect. It will look scattered. So we start looking for that scattered acoustic impedance to help us interpret the log. But again, we're looking at acoustic impedance. We want it to be high, but some cements we pump, it's low. But if it's low, we want it to be variable. And when we run the derivative of it, which tells us about the variability, we want it to start filling in the gaps, as we see here. Besides acoustic impedance, probably the number one reason that we have the ultrasonic log, why it is successful, is to find small channels. Here's an example of a small channel. I think you can see it. A small channel is small because it's a small flowing volume. It may be high pressure, but there's not a large volume. So it's going to slowly move, and as it does, it's going to find its path of least resistance, and it's going to look like fluid flow finding path of least resistance. It's going to look like a river or a creek as it finds its path. Or if you were to spill some of your coffee on the table, it's going to run off the edge of the table in a path of least resistance. It's going to find the little places to go. And so we can see that. See the blue channels. This is classic. Where is it flowing? It's flowing 180 degrees on the other side of what we call a galaxy pattern. Galaxy patterns, you see the little circle there, that occurs because of interference of waves when the casing is very close to the formation. When it's close to the formation, we start getting interference from the formation. We get constructive and destructive interference, which brings us to the knowledge that that is the low side of the hole. And who would have thought the flow is occurring on the wide side of the hole? Very common Occurrence because wells flow on the wide side because though that is the path often of least resistance. Here again, you can see channels on the right. Once again, you see the channel occurring opposite that galaxy pattern. Once again, we're looking for those small river patterns. This one's a little more complex, but we're looking for those small river patterns. This is my own video show. I happened to be out on that well while we watched the gas percolate and while we ultimately shut off that gas. Here's the ultrasonic for that well. When I see these kind of ultrasonics, I get excited. I go over and we'll have to deal, what you're seeing over there is not the eccentricity, it's the azimuth of the eccentricity. So don't worry about all the lines on the left. I'm getting some very high amplitudes at one point when I look at my amplitude curve. I continue to go to the right and I see my radius. We'll talk a bit about casing ovality. I see my features on my thickness of my steel on my casing. And then I go over to my raw acoustic impedance map, pass by that to my bond index, and then I finally get to my cement map. And when I see the cement map, when I saw it on this one, I know where the gas was flowing, at least at this point. I know the gas is flowing very near, well, let's say it's flowing against the casing cement interface, and I pick up those little river patterns. Do you see them? Little rivers. When you see those little bends in the river, it's a great indication that the gas is moving through that channel. And look at it. Those channels, if we're going to take our impedance values, are filled with water, but the gas is percolating through that water. It's not just pure gas coming up through those channels. Water-filled channels as gas percolates through it. We're able to perforate, based on this log, squeeze and shut off that gas. We also see large channels. Again, looking at the acoustic impedance, you can see what appears to be a big cross-flow washout channel. These can be often seen on radio logs. The channels we can pick up with the ultrasonic logs are about an inch. We're now looking at, I'm working with new technology that can see 0.1 centimeters instead of a whole 1 inch. So we're getting much more detailed technologies, but a lot of the technologies can see the big wide channels. The ultrasonic today can probably see about an inch size of a channel. We can see what I call casing signatures. What you see there is a pattern being laid down. You can see the galaxy pattern. That means we're very close to the wellbore. We're getting interference from what happens to be a fast formation here. But you can see an outline of where we're getting interference and where we stop getting interference, and it basically draws an outline of the casing. We can see the casing within the wellbore, which is pretty neat. Do I have isolation here? Well, in between the galaxy patterns, very, very likely. You can also see centralizers in here, by the way, and all sorts of things, and we see the galaxy patterns occur in between centralizers as the casing sags in this well. We look for, on the ultrasonic, we look to see centralizers and collars and the kind of bonding we get above and below those collars. This is something more in advanced interpretation, but cements will settle out on collars. Turbulence will occur past collars, and so there's a lot of things we can get and understand when we look at ultrasonics. Channeling's not going on here. but we're getting better bond past collars and centralizers. Very interesting. A lot of work's been done in this area, but we're seeing in this case some pretty interesting. We'll be wrapping up in about 10 minutes, but look what else we're looking for when we're running the ultrasonic log. I just saw a log like this, and everything I'm showing you here is not the ultrasonic case tow log. These are ultrasonic open hole logs. And I wish I could show you. I've got 2 logs I wish I could show you. They're confidential. I cannot. But I can tell you they look just like the log on the left, only they're cased hole cemented logs. One of the first logs I ever read, ultrasonics, looked just like the log on the left. We get tiger stripes. And you can match those stripes up to where you slide or rotate, where you get bit whirl, because in the middle is a picture of the open hole, what the open hole exaggerated looks like. We can pick that up through the cement. So what I'm saying to you is we can pick up signals because of interference. We can pick up signals using the ultrasonic log of the formation. And you will hear again and again with the ultrasonic, we can only see right outside the casing, but we can get indications of the formation, and that can be helpful. These 3 are actual open hole logs of what can happen, ultrasonic open hole. We get breakout where the formation gets oval because of stresses, and we start sloughing in rock. We can get wear, we call it keyhole wear in the formation, or we can get a shear displacement. And we can pick some of those up on the ultrasonic. Here's the ultrasonic log. To the left, we see open hole. To the right, we see cased hole. You can see where we start getting breakout through the ultrasonic. That's helpful because we can start to understand, first and foremost, if I have breakout, I'm able to see it all. I probably have a good cement in that area, although the log may say I do not. It's kind of interesting because in this case, this is our flexural attenuation says bad. Our acoustic impedance says good. We'll talk about that more in advance. We can also see or experience fast formations, again, because of the interference as we reflect off fast formations. You see, here's the fast formation, and you see the change that we get in the bond log, in the radio log, and in the ultrasonic log. We see other formation effects. You see here bedding planes. This is kind of a famous paper that was written, a piece from it, but it shows bedding planes. We're seeing it through the cement. And so it's good to recognize in these cases, this happens to be probably a really good cement job, but we can see things with the ultrasonic, although theoretically we shouldn't be able to. More formation effects. We see the formations as they come in, and due to time we'll kind of move through this, but right here, this happens to be the flexural attenuation curve, but you see the formation coming in against the casing. The tool is affected by microannulus, but severely for gas, not so much for liquid. In this case, we ran an ultrasonic tool in the well. It remained static in the well, and we just pressured up the well. The tool is not moving. We're just getting a different reading for each pressure increase, and you see at a very high pressure, we close the microannulus, and we go from gas, very sensitive to gas, to when we fully close it at 4,000 psi. Very sensitive to gas microannulus. Here again, you can see on the right, there is no pressure. We do a pressure pass, we pressure it up, and you see the better result that we not only get on the bond log, but we get a better result on the ultrasonic. So again, it's just to point out the better. This is with pressure on the casing, artificially inflating the casing, we get a better looking log. Again, because of time, we're going to kind of move through this, but the previous slide was showing you a picture of microbonding. And this is where it gets a little confusing with the log. Again, here are some of the things that we look for in the logs. And I'm showing the difference at the top is a Halliburton log versus a Schlumberger log in the bottom. Again, I like the composite log on the bottom because I can do some interpretation. Where at the top, I like it because we're showing the bond log in a very high resolution gamma, but it's very difficult for me to understand exactly what's going on if I do not have a composite log. But here's some things we look for. In the top, we look for that galaxy pattern. It means we're close to the bottom. We see a fluid channel, once again, meandering on the wide side of the well. We can see the high, dark acoustic impedance versus the low. As we go down to the log below, down on the log below, we see the inside radius. We see low side features. It may be hard to see here, but you can see low side features where the casing may be laying against the formation. You can look at the dark amplitude on the bottom map. And that dark amplitude means something's going on. Well, magically so, we ran a casing scraper in this well down to that point where you start seeing all of that effect. And that effect will translate into a microbonding effect, coloring green. So when you have dark amplitudes, they often come over. Yeah, I don't know if you can see the mouse, and appreciate that, Ahmed, for that comment. Sometimes when we're filming, the mouse disappears. So can you see my mouse floating around? Okay, great. I thought maybe you couldn't. Here's our galaxy pattern right here. You see it? 180 degrees from it, you see the fluid channel. You see the dark high impedance here. Coming down below, you see low acoustic impedance in the blue. Now we're moving to the Schlumberger log. Hard to see, but you see darker colors on the low side here. Sometimes we'll see dark colors and we think that it's cement where it may be formation instead. Here's our casing amplitude over here. We do not like the dark spots. This was an old well. We ran a casing scraper to this point right here, and you can see this would be older paraffin in the well, scale in the well. It affects a lot of things, but one thing it does, where it's dark here, it turns green over here, although you see a lot of green on this log. Sometimes the green, what the green means, low acoustic impedance, but quite variable. And sometimes when you see the green, you have to kind of just imagine that's a mask due to the casing condition, and you have to ignore it. You have to kind of see what is behind it. Now you can't see what's behind it, but you can see what is unmasked. And sometimes we just have to extrapolate that what's behind that green would be this material here. Here's a classic example of microbonding. Everything was green. It masked the entire well. This happened to be a well where we pumped no cement in the well at this point, but it was mistakenly interpreted so because it was totally masked by green. It was low and it was variable. And so we have to be careful when we see microbonding to get a better look at the composite log. We don't have the composite log here. We have the raw acoustic impedance, the bond index, which is almost all green, and then the cement map. That microprocessing actually can be eliminated though. You don't have to run the microprocessing, and you can eliminate the green. And in that case, I think you would have seen all blue and red. This is the actual bond log for that well, and you can see there was no cement, full free pipe amplitude, but we knew there was no cement in there. We didn't pump any. This was the ultrasonic squeeze afterwards. And now we've run a casing scraper. We've got a better look, and we have no cement in this section. This was the squeeze job. Perforated, the cement came up, bridged at a collar, went into a formation. Now we're seeing the squeeze job, but they were squeezing it because they thought they had just a micro bonded, or they needed to get better bonding, when in fact none of the well bore had cement in it. Very quickly, I'm going to show you the isolation scanner. The isolation scanner is an ultrasonic tool. It contains on the back of it, it contains an ultrasonic log. But on the front side, it's going to shoot that ultrasonic log at an angle, reflect off casing cement formation, and be picked up at 2 receivers. So I shoot the sound wave out here, I reflect, pick it up here, it travels up, reflects, picks it up here. And I will compare the differences between these 2 receivers to determine how much attenuation is occurring in this flexural wave. While I'm doing that, I'll do my regular throw the tennis ball on the other side of the tool. Here it is right here, looking at the other side. This is the latest technology. You get an ultrasonic log, but you also get a flexural attenuation log, usually shown in decibels per feet. How much sound per foot is attenuated or dampened. I then combine these 2 and I draw a curve called the solid liquids gas curve. Highly technical, solid liquids gas. And here I will just show brown as cement and blue as no cement. It's I also call it a composite cement map, but it's a solid liquid gas curve. And here's our solid liquid gas, solids, liquid gas. It's flexural attenuation versus acoustic impedance. And I plot using to draw that map. I find out what my attenuation is, my flexural attenuation. Let's say it's 1 decibel per centimeter, and I have 4 megarels, then I will color it solid. I will just say of what's of interest to me is that everything above 2.6 is going to be solid anyway, from almost everything. We have a small area here that isn't, but almost everything greater than 2.6 megarels acoustic impedance is going to color it brown. So the SLG curve, let me say it this way, leans heavily on the ultrasonic log on acoustic impedance, as opposed to what's on this side, which would lean, or up in this area, which would lean heavily on flexural attenuation. So why do we run isolation scanner or flexural attenuation? It would be to capture the ultra lightweight cements, where the acoustic impedance is less than 2.6, yet we're still getting attenuation flexurally. So just understand that it's only a small piece of the pie where we get more information from the isolation scanner. But we do get some other interesting, very interesting information because we're shooting it flexurally, we're sometimes reflecting not just off the first interface, which is the casing, not just off the second interface, which is the cement, but also the third interface, which is the formation. And we can start drawing the casing inside the wellbore. Here's my casing. If you can see it, there's my well bore right here. Here's my well bore. You see I'm E-centered a little bit here. Here I lose it, but I maybe can pick it up. And you start getting to see that third echo interface. Here I see it and I can start making some determinations. If perhaps, because I'm getting good reflection here, I have a channel, but I can start seeing my casing inside a well bore, which may be helpful for interpretation. I hope I haven't gotten too complicated into the ultrasonic, but let's look at a final log and I'll have you interpret the log for me. If you're still with me, help me interpret. I have a bond log. I have an isolation scanner. That gives me, the isolation scanner, an ultrasonic log, acoustic impedance, and flexural attenuation. So let's interpret this log. And what I'm interested in is an area that I need covered, or I want covered with cement, that may be susceptible to corrosion. And that's this area right here. Where on the bond log, well, tell me what you think. For purposes of this interpretation, you see this dark line here. Let's look at everything below it. And so let's interpret this log. Do we have cement here or do we not? What does the bond log say? Do we have cement? Just act as if you didn't have the ultrasonic to help you. Straight lines, no cement. Someone says, yes, we have cement. See, we go back to the bond log. Bond log itself can be quite confusing. We're seeing the amplitude rise. This is 5.5 casing, so this is about free pipe amplitude. But we seem to be picking up, although some of these can be fluid arrivals, we seem to be picking up some formation. You see that? Up here, my amplitude lowers. And so I don't know right now if I have cement here or not. I'm not ready to say. But I understand if you think you do have cement. I understand if you think it is free pipe. What does the ultrasonic say? Here's my acoustic impedance. We didn't get into the colors of the isolation scanner, but blue is not good. Greens and reds are good. Blue is not good. So without doing much interpretation, although see the amplitude here, how it shows up here, but without doing much interpretation, I do have cement here. It is dark brown. According to acoustic impedance, according to a flexural attenuation, I do not. Therefore, the SLG will depend upon that plot, will argue on the side of acoustic impedance greater than 2.6, and will say we have cement. So, do we have cement? Let's interpret the log and then we'll have questions. How do we interpret the log? First step, we construct the well. When we construct the well, we find out that this dark collar here is a stage tool, is a DV tool. There is no packer involved. It's just a port that opens when we do a two-stage job. So we cement the first stage, we open the port, circulate, and cement the second stage. When I construct the well, I look at casing, it's 5.5. I look at casing, we have a stage tool. I look at the cement. when I do the calculations for the cement, I did not pump enough cement. I didn't try to get cement up to this point. When I construct the well, I should not have cement here. If I constructed the well and the well did raise cement, a lightweight cement up there, my interpretation may be different. But when I construct the well, I have no cement. And if you've listened to me interpret before, I will let the well bore interpret the log before the log interprets the well bore. And when the well bore says I have no cement, just for at least a short while, I'm going to believe it. So I'm assuming there is no cement there. But I also, when I construct the well bore, and this is where cementing gets involved, when I cement, I know I have some cement falling. If I didn't have full returns, I might even be pumping cement down. In this case, we did have full returns. But it doesn't surprise me that there may be an area, take a look at this, where my formation waves are a little stronger and then they start getting really hazy and I start seeing what I would assume to be just fluid arrivals. Pretty interesting. But we're not talking about bond logs, we're talking about ultrasonic, so let's close with this. The ultrasonic says there is cement. Second step, as I do that, I compare the two. It changes. Where does it change? It changes not right at the DV, but a little below the DV tool or the stage tool. And I quit a big change above the stage tool. So I start correlating and then I consider, and this is where so much of interpretation comes in. What could be causing the problem? What could be causing the problem that my bond log would say it's bad, my ultrasonic would say it's good, my flexural attenuation would say it's bad? And so I go through considerations, all of the considerations, and one consideration I move to very quickly is what sort of casing condition do I have? Will it bond to the casing? And I find out something that this casing is not casing. This casing is wrapped in a textile epoxy. It's called right wrap, and it's wrapped such that this is not casing cement bond, it's right wrap cement bond. And I learn that my acoustic impedance I'm reading is of my epoxied right wrap, my textile material. You see, instead of covering this with cement, we decided to stop the corrosion by covering it with an epoxy textile. The good news for flexural attenuation, it compares the two receivers. It didn't see the right wrap. One of the reasons we ran this log was to get a good indication of cement in right wrapped pipe, because the ultrasonic was always reading the right wrap. And so you see, by constructing the well and understanding what's happening with the well, we can come to the right interpretation, because ultimately the scanner said there is cement and we know there's no cement. When it came to a choice of believing acoustic impedance or flexural attenuation, it will believe, the SLG curve will believe acoustic impedance. So the ultimate interpretation, there was no cement. And if I could add something just as an extra closing remark, we had corrosion in this well also. Even the epoxied right wrap didn't help. So maybe we should have cemented it. Well, that concludes our time. We moved from basics into more advanced very quickly, but I'll be glad to answer any questions in regards to the ultrasonic log. And thank you very much for your attention and for participating today.
Thank you, Mr. Harris. It was a great session, and we have collected some questions. Hopefully, we can answer as much as we can. The first question, How to differentiate between gas and water in small channels in the cement map or ultrasonic?
Yes, could you repeat that question one more time?
Yes. How to differentiate between gas and water in the small channels in the cement map or ultrasonic log?
Yeah, the question is, to what degree can you see what is behind the pipe when it comes between mud and water? I don't think you can. I mean, if you wanted to get very specific, you could say, we measured a 2.4, which is still blue, but that would be a higher acoustic impedance than water. I mean, water's acoustic impedance, 1 point something. So you could get very specific and look at uh, the detailed data. I don't know if I would do that or if it even would matter so much. In the one log that I showed that was producing gas, what was in that channel changed over time. We started producing gas. What was flowing out of the well was mud and dirty material, and then it turned into water, clean formation water that was then the gas was percolating up with. So that even changed throughout the flowing in that channel, whether it was mud or water. So you could get very exact and try to interpret the difference between different muds and waters by looking at the exact number, but it's quite relative. I don't know if I would be that exacting in my interpretation. Good question.
Okay. Next question. Someone is asking, Mr. Harris mentioned that distinguishing good from bad cement is easy in the ultrasonic log, but not always correct. Why is not always correct?
Yeah, I find it be that it's very first of all, it's very accurate in channels, in seeing various channels. We see that easily on the ultrasonic. We can't see it on the bond log. So I find it detects what's right next to the casing very nicely. So it's very good at that. If there is something on the inside of the casing, that's where I see most trouble. Or, and we didn't talk about this a lot, but if the casing is being pushed by the formation, which makes the casing more oval, which makes two sides of the casing really strong bond and maybe two sides less strong, then you start seeing different bonding, but you still have to make a good interpretation. It's not so clear. Is it that no cement is there, or is it just more bonded on one side? Or if there's something on the inside of the casing, it starts to mask the results and is a little more difficult. So I believe if someone asked if you could run only one tool, what would it be? That's a hard question because it's according to the situation, but many people would say the ultrasonic. I would always say ultrasonic with the CBL in tandem gives me my best interpretation. Others are going to argue, and we could argue about Baker's tools or uh, radial bond logs and other degrees, and we could have our debate about which is the best data and which is the easiest to interpret. I'm speaking strictly of if I have to interpret what is going on in the well, then I get my best interpretations when I have the ultrasonic and the CBL. And if I had to only choose one, I would groan. I wouldn't be happy, but I would probably, it used to be the bond log because I just like reading bond logs, but it would probably be the ultrasonic log. Still, it has its limitations. It can be masked, and some things can occur which affect the casing, affect the sound wave. I have to be aware of those limitations.
Okay, next question. Can we run caliper log with ultrasonic to use it as a quality control for the casing radius?
I think the answer is yes, you can. I mean, we have several ultrasonic calipers, so obviously this tool, as we run it in this mode, you can actually run in casing evaluation mode versus, I'm just talking about the variety of ultrasonics that we have. So yes, it can be. Obviously, if we're doing it for cement interpretation, that is not our number one intent, but we see that information. So I think there are other electronic calipers that are maybe more efficient in that way. I don't know. I'm not an expert in that area. But yes, this does give you a caliper for the casing, for sure.
Okay, and last question. What are the disadvantages of ultrasonic lock in modern era?
Yeah, that's a good question. You know, um, there is a disadvantage of all current logs, so I'll throw that in with debonded cements. I think we pick them up better. I do with the ultrasonic, but it still can be misinterpreted because we're looking for that perfect coverage. I think disadvantage would just be that we get often what you get is just the log. You may not get a composite log like we're showing here, and you have to trust what you get. I received a log recently. It's a confidential log I received from an oil company, and they couldn't figure out what was going on. Why was the cement so bad? And it happened to be that they were using the wrong, processed it incorrectly. They were using the wrong fluid velocities. They put a theoretical in and it was showing no cement. When they put in the correct one, it all showed up. It's a highly processed log, so it has to be well quality controlled. And that would be the big disadvantage where the bond log, you see the VDL, you can make some quick determinations, but it's a very useful tool, but it's highly processed. And I'm not saying that happens very often. Most of the ultrasonic logs I look at and I get are very well QC'd and ran. So it's not a big problem, but just trusting the cement map and not knowing what's behind it, that's difficult for some of us interpreters to do.
Okay. Thank you, Mr. Harris, and thank you all. The session will be uploaded on PioPetro YouTube channel, and don't forget to solve the quiz on Google Classroom. Best of luck, and thank you again.
Thank you very much.